In Lean, when we talk about flow, we usually talk about takt time and how well we can consistently achieve takt time. And we're going to start from an idea coming from production physics. And first of all, it can also apply to service physics as well, but the idea behind takt time is how fast am I required to work on each step in order to accomplish what customers are asking for. And the common way to think about this is if I'm producing 24 cars in a day because demand is 24, then my takt time is 1 hour, which means every hour I need to be producing a car for 24 hours. If I operate at 8 hours, that's 3 cars per hour, which would be a takt time of 20 minutes per car. So that's the idea behind takt time. So it's daily operating time divided by required daily quantity. Other 3 definitions in order to get to production physics calculations for Little's Law is cycle time, which is the actual time from when I start producing something or providing a service to when that service is concluded or when that product is done being built. And that's the cycle time from beginning to end. What's the average time it requires to go through all the process steps? Throughput is a little different. Throughput can be applied to the system as a whole or to a particular step in the system. And throughput is the rate of output. Sometimes it's called the throughput rate or throughput time, although some of these definitions get sort of shady. In the Lean Production Simplified book, we have some good definitions there. And lastly, WIP, and I think pretty much everyone understands that. WIP is work in process. And work in process in a service environment is probably best understood as in a healthcare environment, because WIP in healthcare could be number of people waiting in a room for their next step of their care, or waiting in a queue to receive the next blood test or something of that sort. That's WIP in a service environment. WIP in a production environment is some half-completed product in between the beginning and the end, and that's total WIP in between those beginning and end points. So now we can talk about Little's Law. Little's Law is a relationship similar to in physics when we know force is equal to mass times acceleration. It's that fundamental relationship that defines how the rest of the physics math works. So with Little's Law, we have cycle time and throughput and WIP in this relationship, where cycle time is WIP divided by throughput. And you think about throughput rate, it's the time at which I work through my WIP. That's my cycle time. And my throughput time is WIP divided by how long it takes me to do each item. And so that would be my throughput rate. So that seems to make sense if you think about it mathematically. A better way to think about it and why we're looking at this is suppose I increase at the rate at which I produce throughput. If I increase my throughput rate, that generally increases my work in process or decreases my cycle time, or maybe a little of both. If I increase WIP, that allows for increased throughput. That doesn't mean I do, because my rate won't increase just because I have more WIP, but it allows for increased throughput because there's more things to work on, and it increases cycle time. The more WIP, the longer it takes in a first in, first out environment for things to get through the system, so my overall cycle time would increase. And lastly, if I can decrease my cycle time, this is the best option. It increases my throughput, so I go things at a faster rate if I'm decreasing my cycle time, and it also decreases WIP. And so in the Lean method, we are really focusing on decreasing the cycle time overall, and that's really what eliminating waste does. So within those relationships, we have these different laws, which are part of Little's Law per se, where the law of variability says that as you increase variability, it inevitably degrades the flow or degrades the performance of a system. And because this is a production law or production physics, we say a production system, but it just as easily relates to services. And law of variability buffering. Variability in a system will be buffered by something, usually a combination of inventory, capacity, or time. And so if there's variability, there will be buffering naturally, and often those buffers are waste. So the more variability there is in our system, likely the more waste we'll see, because the waste allows us to cover up the mistakes that we're making. And lastly, to achieve flow, we're really talking about decreasing variability in order to make flow more achievable. So there's lots of ways that we can do this in Lean. We have muda that we want to eliminate. And so muda is an obstacle to our flow. We can think of changeover time as an obstacle. I have to stop what I'm doing, wipe down an operating room, clean everything up, put everything away, bring the next patient in. All of that decreases my flow. That's a changeover in a medical environment. Also in a machine environment, if I have to change over parts to produce a new product, that's a changeover as well. Machine availability is an obstacle. If things break down, it stops my production. Also quality problems. Every time I have a quality problem, that's something that doesn't actually accomplish what I set out to accomplish, and it wastes time doing something that doesn't achieve our outcome. And so there's a lot of different things that we can look at as obstacles to flow. Some of the common obstacles are just space between a process or time between steps. And you can see how all these relate to the inability to achieve flow. And so a good way to start achieving flow, and some of these things we've discussed already, first would be to define the value from the point of view of the customer. And we did that early on. Also, a simple approach is to move machinery and people closer so the value can be provided continuously. And then subordinate everything to numbers 1 and 2. Now, if we were in class, we were going to do an exercise, and I apologize that the snow came. I should have worked out the weather situation, stopped the snow somehow. But I was going to have us look at that example in the book about the shoulder problem that the woman was having. And how would you redesign the healthcare system to achieve flow? So throw everything you know about healthcare out the window. How would you change your experience in a healthcare environment to make sure everything flowed from one step to the next? What would be required, technology-wise, infrastructure-wise? And we, last time I did this in class, it was a really nice discussion about what are the limitations and what are the opportunities to achieve flow in a medical environment. And the students, MBA students, were able to actually redesign some ideal, albeit nearly impossible to accomplish right now, ways to deliver healthcare. And I think it's fascinating when you start throwing things out the window and saying, what would we do if it was a perfect world? And there could be a lot of opportunities that we're not aware of as we brainstorm and innovate. So, conditions for continuous flow. First condition, everyone has to be able to do everything. We have to be able to be flexible. So if there's ever a hiccup, someone can jump in and help. So people should be cross-trained. In some cases, this is impossible, especially in a service environment where sometimes the skills are very difficult to come by. Machines must be operational. So they need to be fixed, they need to be maintained, they need to be ready to go. Think of a changeover. It needs to be set to go as soon as possible. Work should be standardized, and it should be standardized by the people doing the work so that they know how best to accomplish it, and it's done in the way that they would normally do it. Self-monitoring is one of those conditions related to quality. I want to be able to have it be fully contained so I don't have to stop and inspect something. The process itself monitors and stops problems from occurring. Visual controls are helpful. They help to establish continuous flow, such as 5S, and-on boards, performance feedback, things like that allow me to know how to adjust to make sure flow is occurring. Large batch machine workarounds. I mentioned the changeover process. That's basically what SMED is. That's really changeover. Stock buffers is another one. The book mentions Taiichi Ono doesn't like inventory, but knows that it's important and required in some cases. And so if we have a large batch machine, we've got to have stock in front of it to make sure that it never stops because of lack of inventory. Work balance, we mentioned takt time. If we can balance our work based on takt time, the flow is achieved much more smoothly. And so we almost rebalance or redesign work so that it falls under the approved takt time each step. Lastly, the most obvious one is move things around so they're more close. And that makes us flow things faster because we don't have to walk so long or transport things so far. So these are just some conditions. And when we look at this list, there's a lot of problems, a lot of things that need to be adjusted. And that's why also this week we're talking about problem solving and the A3 process, which I'll cover in the next video.